Hello, everybody, and welcome to my second lecture of this chapter. This is my ionic bonding lecture. We're going to be talking about the formation of that, a little bit on the energies, right? We have the lattice energy as well as a practice, just like always at the end. Okay, so starting by looking at the formation of ionic bonding. So think about our ionic substances that are made of a metal and typically from the left side of the table, so from the S block, and then a non-metal from the right side of the table, from the P block, and probably not a noble gas because the noble gases are pretty stable. Right? So let's say you have something like sodium, which is a metal, and then chlorine gas, right? That's an example of non-metal. They are getting closer to each other. They're going to be a conversation between these two, and that is how they can make sodium chloride, which is a very stabilized ionic compound, right? So here's a reaction. My sodium solid, this is naturally solid, interacting with chlorine gas, we are forming 1 mole of sodium chloride. And if you look at your delta H formation, it's a negative value. It's an exothermic process, so we are releasing this much energy when we are forming 1 mole of sodium chloride. Okay, so we're going to go deep into the discussion of energy, why we have exothermic, how we can understand that on the next few slides. Okay. Okay, so think about the formation of sodium ion from sodium and chloride from chlorine gas. This is going to be involve electron transfer. Sodium is going to lose an electron and chlorine is going to gain that. This means that we should talk about two important properties, right? The first one is your ionization energy. How easy is that for the sodium to, let go of electron? And the second one is the electron affinity, which is the tendency to gain electrons for chlorine. Okay, so sodium chloride is going to be formed because sodium has low ionization energy, so it's easy for that to, let go of electron. And chlorine has high electron affinity, making this typical ionic compound possible, right? Now we can use the Lewis electron dot symbols to present the reaction. So what I have here is I have my sodium where we have only one electron, only one valence electron, and that valence electron is going to be added to the valence shell of chlorine to make it as chloride. Okay, cool. Okay, so let's continue our discussion on this reaction. I can use the arrow here to present the electron transfer from sodium to the chlorine atom, right? And each of these ions now has an octet of electrons. They all have the closed shell configuration, and you can see them by their electron configuration as well. And we typically use the, square bracket around the anion to present that we have, the 8 electrons located on our chlorine, okay? Now, as you remember, we mentioned that this reaction, which is presenting the formation of sodium chloride, is an exothermic reaction, right? This is the delta H formation for sodium chloride, which is a negative value, right? So this is an indicative of, stability of these compounds. When they formed, they're going to release energy, right? So typically the formation of our ionic compounds are going to be exothermic. And the main reason is the attraction that we have between the two, oppositely charged ions, right? The cations and anions, okay? So looking at the next page, however, if you think about the electron transfer that we mentioned from sodium to chlorine, right, this is going to be involved in two steps. We have the endothermic step, which is removing of an electron from sodium. That's your ionization energy, right, which is about 500 kJ per mole. That's an endothermic step. And then I also have the exothermic process, which is adding an electron, right, to chlorine. And this is going to release about 350 kJ per mole. So if you add these two energies, right, the sum is going to be about 150 kJ per mole, which is a positive energy, right? So it seems that I have an endothermic process when you are adding these two energies, right? And that does not make sense, right? Because we said that the formation of sodium chloride is an exothermic process. So how we can understand that? When you're looking at these individual you know, ions, the cations and anions, we do not consider the strong electrostatic attraction between them. When we are forming an ionic compound, right, we need to consider that these two ions are going to be strongly attracted because we have the electrostatic attraction, and that is going to be presenting the stability of these solid structures, which is known as lattice energy. Right, so the lattice energy measures how much energy is released when the ions getting closer to each other to form the solid, and that is the main reason for stabilizing these ionic compounds. Okay, I hope that makes sense to you. We're going to have more about the lattice energy on the next few slides. Okay, so by definition, the lattice energy measures how much energy is released when the ions are getting closer to each other to make your ionic compound. Okay, so in order to understand that, you can imagine that you have your sodium chloride and you try to pull them apart. How much energy I need to add, right, to pull these two completely apart? That is going to be about 780 kJ per mole. This is known as your lattice energy, right? You start from your sodium chloride and you try to pull them apart in order to turn them to their cation and anion, right? That must be an endothermic process because we are adding energy to take them apart, right? Then the opposite process, right, which is, joining of these two ions to form sodium chloride, must be an exothermic reaction, right, which is going to release this much energy to make your sodium chloride. Okay, cool. So in summary, the energy released by the ion attraction makes the formation of the ionic compounds exothermic, right? Despite the fact that we have endothermic ionization energies. The strong attraction causes the ionic compound to be hard, brittle, and they typically have a very high melting point. For example, for table salt, sodium chloride, it's about 800 degrees Celsius. That is crazy high, right? Now, if you try to do the calculation for the lattice energy, we need to consider their charges, their sizes, and the way that they are arranging, right? So generally speaking, the lattice energy increases when we have higher charges and a smaller ionic radii. The electrostatic potential energy, by the way, that you have seen it before, we can use that again to understand the interaction between the two charges, right? And as you can see, we have the charges on the top. That means the higher the charges is, the stronger the potential is. And then we have the D, which is the distance between the two ions, and the potential is going to be inversely proportional to that. Okay, I hope you remember this equation from our previous lectures. Okay, cool. That's it. We just need to do the practice together. Bear with me. Okay, so here's the question. Arrange the ionic compounds sodium fluoride, cesium iodide, and calcium fluoride in the order of increasing lattice energy. Okay, so I'm going to start by looking at their charges. For sodium fluoride, we have sodium and fluoride, and they both have one positive and negative charge, right, respectively. For cesium iodide, again, we have, positive, negative charge. But for calcium oxide, we actually have calcium 2 plus, oxide with 2 negative charge, right? And remember, charges are going to be typically more effective, right, than the distance. And you can say your calcium oxide is going to have the highest lattice energy because it involves, 2 plus, 2 negative charges. Okay, so that will be the strongest one. Now, between the other two, looking at sodium fluoride and cesium iodide, we have pretty much the same charge, right? But cesium is larger than sodium and iodide is larger than fluoride, right? So since larger ions result in a weaker attraction, cesium iodide has the lowest lattice energy. Okay, so I can put them all together. Cesium iodide would be the weakest one. Then we have sodium fluoride, and calcium oxide must be the strongest one. Excellent. Thank you very much for watching this video. If you like it, give it a thumbs up. There are going to be a lot more coming up soon for you. Take care of yourself and see you on the next video. Bye-bye for now.